and we'll be discussing a few questions. Okay, and these questions have already been uploaded into your week 5 folder, and you can find them there along with the solution as well. Okay, so let's go straight to practice question 1. We have helium gas entering a converging diverging nozzle at 0.7 MPa pressure, 800 Kelvin temperature, and 100 meter per second velocity. So what are the lowest temperature and pressure that can be obtained at the throat of the nozzle? So this is how a converging diverging nozzle typically looks like. We have to find the properties, meaning temperature and pressure, at the throat. Okay, and we have just the equations for that. Of course, we have to make these standard assumptions that helium first is an ideal gas with constant specific heat, and that the flow is one-dimensional and isentropic with a constant mass flow rate. Okay, that's steady flow. So we find the properties that we need. Okay, if you have tried the previous exercises or examples, you will know that you need to find the specific heat ratio K and the specific heat of the gas. Okay, both are from table A2. So we find these values. You can pause the video and find them from the property table to verify these numbers. Okay, so the lowest temperature and pressure, since the question asked for lowest temperature and pressure. Okay, so the lowest temperature and pressure that can be obtained at the throat are the critical temperature and critical pressure. Okay, so to find the critical temperature and critical pressure, we have these two equations, right? We learned this in the previous video. So if you look at these equations, you will see that you need T0 or stagnation temperature and K for temperature, and then for pressure we need stagnation pressure and K. So of course we have K, we just need to find the stagnation properties first. Okay, so for T0 we have this equation. You've used it before, and for P we have this equation. Okay, so what else are we missing in order to solve this? We have velocity. Okay, given specific heat we get from the table. Of course, static temperature and static pressure we have here. So I don't think you have any problem to solve. Okay, so plug in the values. You should get stagnation temperature is 801 Kelvin. Again, I strongly encourage that you pause before you see the numbers so that you can see where you get it wrong. Okay, and I'm going to mention this again, that whenever you're dealing with a velocity, always remember to convert. Okay, when you have velocity and a unit of energy there, kilojoule, then you need to be careful. Okay, because V squared will typically give you joule per kg. So we need to get it the same unit as the specific heat value, specific heat dimension, which is kilojoule per kg times temperature here. Okay, so the conversion is necessary, dividing by 1000. Okay, and then proceed to find pressure. This one, of course, you don't have to convert. Please always use Kelvin as the temperature. And then once you have these two values, you can find the critical properties. Just substitute into this equation and you get the final answers. Okay, so very straightforward. Okay, this is question 2. I'm gonna let you try this question yourself. Okay, there are two parts to it, similar, but for different types of gases. First is air, and at certain state and properties. The second is helium, but approach is the same. So you can try this. Solution is available in the lecture notes. Same thing here. I'd just like to explain that this word quiescent means dormant, inactive. Okay, so inactive CO2 at so and so is accelerated isentropically. You can try this question. Solution is provided in the lecture notes. And we are going to do two more. Okay, question 4 and 5. So practice question 4 goes air at 200 kPa pressure, 100 degrees temperature, and Mach number of 0.8 flows through a duct. Calculate the velocity and the stagnation pressure, temperature, and density of air. So we have to find velocity, stagnation pressure, stagnation temperature, stagnation density. So you may recall that you have all these formulas ready to be used. Okay, but first the important assumption is that air is an ideal gas and that it has a constant specific heat at room temperature. That's the value we're going to use. And you take the values from the property table, you get the gas constant and the specific heat ratio. Okay, I've mentioned it before that I think for air you should have memorized these values by now. Okay, we used it a lot in thermodynamics, and here you will see air being used the most. Okay, so you can memorize the value of R and K for air. Okay, so now first is velocity. We have this equation. This is simply from Mach equals to V over C. So just rearrange, find V. But to find V, we need the Mach number and C. We don't have C. Mach number is given in the question. So C square root KRT, we have K from property table, R is from property table, T is the static temperature given. Where is it? Here, 100 degrees. Okay, so what's happening here is 100 plus 273. 273 is good enough. Okay, the more accurate will be 273.15, but I'll accept 273. Okay, and again, C is a velocity, so you need to times 1000. Otherwise, you'll be getting a very small number, and then that should be the clue to tell you that you forgot to multiply by 1000. Okay, so with the value of C, we put it into this equation and you can find velocity. Okay, next for the stagnation properties, we have these three equations. This is from the earlier part of last week. Okay, stagnation properties, you can rewatch the video if you need to. So these are the equations that we can use. Okay, but these are stagnation properties expressed in terms of, in the case of temperature, here is Mach number. Okay, not expressed in terms of velocity. Okay, so we have developed this equation in one of our previous videos. Okay, so we have all the values, static properties. Hang on, we don't have density. We have temperature, we have pressure. We have K, Mach number. Okay, so you have to find T naught first. We have 421. Okay, so with that, you bring it here. We have this value. We have the static temperature. Again, everything has to be in Kelvin. K, of course, you have that. Substitute, and we get this as the stagnation pressure. Okay, so finally for stagnation density, you need the static density. What is the density of air entering through the duct? Okay, what's the density here? We don't have that, so you have to find that, of course, using the ideal gas equation. Okay, PV equals to MRT. Density equals to mass over volume, therefore P over RT. Okay, so P is 200 as given in the question. R is the gas constant, T is the given temperature in Kelvin. So 273 plus 100. Alright, so get density of air and put it into this equation. This is your T naught that you get from here. This is the given temperature, K, and then you get the stagnation density. Okay, again, I think all the questions here are quite straightforward. It's just a matter of finding the right values and knowing the difference between, for example, static properties, static temperature, stagnation temperature, and critical temperature. Okay, the last question is an aircraft is designed to cruise at Mach number 1.4 at 8,000 meters elevation. Okay, and at this point, the atmospheric temperature is 236.15 Kelvin. Determine the stagnation temperature on the leading edge of the wing. Okay, what would be the stagnation temperature on the wing of the aircraft? So stagnation temperature, okay, of course, standard assumptions. Air is ideal gas. Actually, this whole chapter is based on these assumptions. Yeah, that the gases that we're dealing with are ideal gases and they have constant specific heat values that we will use. Okay, otherwise, you know that the specific heat value changes with temperature. Okay, so we have to use the exact value if you want to be more accurate, but to keep it simple, we make this assumption. Okay, so of course the aircraft is flying in air and it has this gas constant, Cp value and K from table A2. So you can pause and go and verify these values. Okay, so stagnation temperature, what you actually need ultimately is this with this equation. Okay, one of the earliest equation we looked at last week. So this is the version expressed in terms of velocity. Alright, and then to find this, you have one property missing there, which is velocity. We find velocity first. Velocity is Mach number times sonic velocity, sonic speed. So that is from this equation, of course. Okay, and to find this, we need C. We have Mach number, yes, but we don't have C. So we find C first. C equals to square root of KRT. K and R are from the property table. And then T is the temperature. The static temperature is given in Kelvin already. So you can just use this value. Don't forget to times 1000, you get final answer for C. So put that here. And then the velocity of the air will be 431.2 meters per second. Okay, of course, it's expected to be higher than C because Mach number is more than 1. Okay, so with that, you can find the stagnation temperature. So put in your value for T, it's given here in the question. V is what you got here, V squared over 2 Cp. Cp is from property table. Don't forget, anytime you deal with velocity, square divide by 1000. Okay, and then we get the final answer. Okay, that's it for the practice questions for this week's topics. I hope you will try the other two that I have left in the lecture notes, so the solutions are there as well. Okay, thank you.